All right. Well, of all the calculus that you ever learn, the most important thing in as far as real life applications go is differential equations. Especially when you become a core technologist, then you sneeze and you have to solve a differential equation. You blink and you have to solve a differential equation. So it's essentially a core technologist is permanently married to differential equations. What we learn at this point of time is the very basic elementary kind of differential equations. At your level, there isn't a world of things in differential equations. There are a few compact forms or few given things in differential equations. You end up mastering those things, and we are done in as far as our +2 syllabus on differential equations is concerned. Now, what's essentially a differential equation? What's a differential equation? It's an algebraic relationship in which derivatives and functions are involved. For example, d2y dx2 dy dx y plus sin x equal to 0. This is a differential equation. A relationship between the various derivatives, the function, etc., the independent variable x, the dependent variable y, all put together. A relationship connecting all of them is a differential equation. There are two kinds of differential equations. The ordinary differential equations, which is where our focus would be at this level. And then there are partial differential equations, PDEs. The ordinary differential equation has just one independent variable. For example, this is an ordinary differential equation. The only independent variable here is x, right? An ordinary differential equation, this is an ordinary differential equation, only one independent variable. That's an ordinary differential equation. And then we have a partial differential equation, PDEs, in which there are two or more independent variables. For example, I have dou y dou x plus dou 2y dou z2 plus dou x dou t equal to 0, for example. This is a partial differential equation. In which there are three independent variables, x, z and t. X, z and t are three independent variables. Two or more independent variables will constitute a partial differential equation. One independent variable will constitute an ordinary differential equation. All right. Now, let's get familiar with a little jargon associated with differential equations. Can I wipe this off? So focus would be on ordinary differential equations that would involve only one independent variable. In this case, the only independent variable, like I told you, is x. X is the only independent variable. Y, of course, you realize is the dependent variable here. X is the independent variable. Two things relevant as far as ordinary differential equations go. Number one, there is what's called the order of the differential equation. The order of the differential equation is the highest order derivative appearing in that differential equation. The order of the differential equation is the highest order derivative appearing in the differential equation. For example, look at this. For example, this is a differential equation of order 3. The highest differential coefficient appearing here is of order 3. So this is a differential equation of order 3, for example. This is a differential equation of order 3. And then the second thing which is relevant for differential equations is the degree of the differential equation. What's the degree? Write down. The highest power of the highest order derivative, that appears in the differential equation, after it is freed from all radicals and fractions. Now what I mean is, suppose I have a differential equation of the following kind. Suppose this is a differential equation. First of all, what's the order of this differential equation? 4, because the highest order derivative appearing here is 4. So the order of this differential equation is 4. Now, the order of the differential equation appearing here is 4. Now, what's the highest power of the highest order derivative here? See, the 4th derivative is appearing here as well as here, but the highest power is 2. Although the highest power of all derivatives put together is 6, but what we are seeking is the highest power of the highest order derivative. That's 2 here. So the degree of the differential equation is, the degree of this differential equation is 2. The highest power of the highest order derivative. The highest power of the highest order derivative, that's the degree of the differential equation. Now when I say you got to free it from all fractions and radicals, suppose I have a differential equation dy dx to power 1/3 is d2y dx2 to power 1/4. Suppose I have this kind of a differential equation. Okay. As far as the order is concerned, you don't have to free it from radicals and fractions. The order of the differential equation is 2, because the highest order derivative appearing here is 2. So the order is not the problem. The order here is 2. But then you got to free it from these radicals. To free it from these radicals, raise both sides to the power 12. So if you raise both sides to power 12, this would be to power 4, this would be to the power 3. Yes or no? If you raise both sides to power 12, then you free it from all radicals, isn't it? And once you do that, realize that the highest power of the highest order derivative here is 3. So the degree of the differential equation is 3. Degree of the differential equation is 3 here. right? Now suppose I have a differential equation of the following kind. dy dx, or rather let's say x squared dy dx equal to dy dx minus dy dx whole cube by 3 factorial plus dy dx whole to power 5 by 5 factorial minus dy dx whole to power 7 by 7 factorial plus so on so forth, plus so on so forth. A differential equation of this kind. In this case, one thing is obvious, the order of the differential equation is 1, because the highest order derivative appearing here is 1. That's the order of the differential equation. That's the order of the differential equation. But there is no degree of the differential equation. In this case, the degree of the differential equation is not defined. Is there any highest power of the highest order derivative here? No. So the highest power of the highest, it's an infinite series going this way. The highest power of the highest order derivative is not appearing here, is not defined, right? So the degree is not defined here. So you can have a differential equation in which the degree is not even defined. The degree may or may not be defined in a given differential equation. In fact, do you realize that this right hand side is in fact sine of dy dx? Do you realize that the right hand side is in fact sine of dy dx? T minus t cube by 3 factorial plus t to the power 5 by 5 factorial and so on and so forth. That's the expansion of sine theta, sine of dy dx equal to x squared dy dx. So this differential equation does not have a degree, but it has an order which is 1. Clear? So you clearly understand what an order means, what a degree means. And there could be situations where the degree may not be even defined for a differential equation, but the order will always be defined. You will always have the highest order of derivative appearing in a differential equation, so that will always be available, right? But in most cases that we are going to deal with, both order and degree would be very well defined, would be available to us. All right. Now once we understand order and degree of a differential equation, let's figure out how a differential equation is formed actually. Let's understand how a differential equation is formed given the equation of a certain curve. Given the equation of a certain curve or a family of curves. We could be given a family of curves. What is it that I mean by a differential equation of that family of curves? Now, family of curves, what is it that means? It means family of curves. If I have a function of x and y that involves n arbitrary constants, the n arbitrary constants are a1, a2, a3, an, that equal to 0. The moment I say these are n, see there is difference between arbitrary constant and a fixed constant. An arbitrary constant could be assigned different values, but a fixed constant cannot be assigned different values, right? See, when you integrate a function, for example, when you integrate cos x, you get sin x plus c. Is that a fixed constant or an arbitrary constant? That's an arbitrary constant. That's an arbitrary constant. But when you say y equal to sin 2x, is this 2 a fixed constant or an arbitrary constant? That's a fixed constant. So you must draw a very clear-cut distinction between a fixed constant and an arbitrary constant, right? So if I have a number of constants in a equation that involves x and y, and each of these constants could be assigned different values, then these constants are referred to as arbitrary constants. These are arbitrary constants. So this in general represents a certain curve, a family of curves. Why a family of curves? Because these a1, a2, a3, an are arbitrary constants. These are arbitrary constants. For different sets of a1, a2, a3, an, you get different curves out of it. So what it gives us is a family of curves, as long as we enjoy the liberty to vary a1, a2, a3, an, treat them as arbitrary constants. For example, I can have, let's say, a curve like this, y minus a1 whole squared equals 4ax. Suppose a curve is given of this kind. See, this is eventually, when I write it this equal to 0, it's a function of x, y and a1. Now this a1 I treat as, if I treat as an arbit constant, if I treat a1 as an arbit constant and this a as a fixed constant, then I can't change this a, but I can change this a1. I can change a1. I can't change a, it's a fixed constant, but I can change a1. What would it then represent? A family of parabolas. It will represent a family of parabolas having the same lattice rectum 4a. They have the same lattice rectum 4a, but with a variable vertex. With a variable vertex. The vertex is 0, 1, 0, 1.5, 0, 2.5 and so on and so forth, right? This is varied, right? So this, for example, is a family of parabolas with a fixed lattice rectum, but with a variable y coordinate of the vertex, right? So this is family of parabolas whose axis is parallel to the x-axis, Now, how do I constitute the differential equation for this family of curves? How do I constitute? I want to form the differential equation that would represent all members of this family independent of a1. When I say form the differential equation of this family of parabolas, family of curves, I'm looking at a relationship that would be true for all members of this parabola, family of parabolas. That means it would be independent of a1. That's a relationship that I'm seeking then, right? Now, how do I arrive at that relationship? That means if I'm seeking a relationship independent of a1, I would have to eliminate a1, find a relationship. After having eliminated a1, what I do is, let me differentiate both sides, let's say with respect to x. What is it that I get? 2 into y minus a1 dy dx minus 4a equal to 0, right? Now this y minus a1 I can write as root 4ax plus minus root 4ax. Yes or no? I can write y minus a1 as plus minus root 4ax. So this y minus a1 could be written as plus minus root 4ax. So this would represent the differential equation for this entire family of parabolas. Now, how many constants were there in this equation, in this family? There was just one arbitrary constant a1. There was just one arbitrary constant a1. What's the order of the corresponding differential equation? 1. Realize that the order of the corresponding differential equation is 1. Alright. Suppose I have a family of curves of the following kind. xy equals say a e power x plus b e power minus x plus x squared minus 2, where a and b are arbitrary constants. Suppose a and b, it's given. Somebody would have to tell you that they are arbitrary constants. Are arbitrary constants. A and b are arbitrary constants. So if a and b are arbitrary constants, you have the leverage to assign different values to a and b and therefore arrive at different members of this family of curves. Now my question is, I want to constitute the differential equation representing this entire family. I want to constitute or form the differential equation representing this entire family. That means all members of the family must be represented by one common differential equation, right? Implying that I would have to in turn find a relationship that would not contain a and b, the arbitrary constants. If it does not contain a and b, it would be true for all members of the family, right? So what I do is, let me differentiate both sides with respect to x. Let me differentiate both sides with respect to x. Here we have two arbitrary constants. In the earlier case, we had one arbitrary constant and we got a differential equation of order 1. Now we have two arbitrary constants and let's figure out the order of the corresponding differential equation. Alright. So let's first get the differential equation. Let me differentiate both sides with respect to x. This. Let me differentiate a second time with respect to x. Let me differentiate a second time with respect to x. When I do that, this is what I get. When I differentiate a second time, this is what happens. But a e power x plus b e power minus x, which I have got again, is like xy minus x squared plus 2, right? A e power x plus b e power minus x is xy minus x squared plus 2. Right? So then, this is my new differential equation. 2 dy dx plus d2x d2y dx2 is xy minus x square plus 4. Have I freed it from the two arbitrary constants a and b? And what's the order of this differential equation? 2. The order of this differential equation is 2. In fact, in general, the number of arbitrary constants would be equal to the order of the differential equation. Would be equal to the order of the differential equation. The order of the differential equation would be equal to the number of arbitrary constants that appear in the family of curves. Not fixed constants but arbitrary constants. That's very important to know. That's very important to know. Great. So all members of this family would subscribe to this condition. So this is the representative differential equation for this family. Clear? Suppose I said, write down find the differential equation, for the family of circles, find the differential equation for the family of circles whose centers lie on the y-axis, all of them having the same radius, Now, first of all, what am I talking of? I'm talking of circles with centers on the y-axis, right? And having a constant radius a, having the same radius a. So a circle with center on the y-axis, would be x squared plus y minus k whole squared equal to a squared. This is a circle whose center is on the y-axis 0 comma k and whose radius is a. Now, the family that we are talking of is one in which a is a fixed constant, same value, but k is a arbitrary constant. Right? So in this case, a is a fixed constant, whereas k is an arbitrary constant. So in order to find the differential equation, what am I entitled to eliminate? K. Right? And since there is one arbitrary constant, you would expect the order of the differential equation to be 1. So in any case, let's go ahead and differentiate both sides with respect to x. So when we differentiate both sides with respect to x, we get like a 2x plus twice y minus k dy dx equal to 0. Right? I got to eliminate k. Realize that I could write y minus k as plus minus root a squared minus x squared. See, y minus k could be written as plus minus root a squared minus x squared, which I can plug into this and dispense away k. So then we get like a x plus minus root a squared minus x squared dy dx is 0. That's the differential equation. That will represent family of circles with center lying on the y-axis and having a constant radius a. Right? That's the required equation. In general, when you have a certain curve f, a function of x, y involving n arbitrary constants a1, a2, a3, an, what you would have to do is you would have to differentiate n times. So you differentiate once, and you get one equation. Differentiate this with respect to x, you get one equation. Differentiate twice, you get a second equation, and then you differentiate n times. And you get the nth differential equation. You get the nth derivative, right? You differentiate n times, you get the nth equation. Now, from these n equations that involve a1, a2, an, you solve for a1, a2, an. And once you solve for a1, a2, an, you plug into this original equation.